In this lecture, we will be going over resampling methods. For this lecture, you should have read Chapter 5, Resampling Methods, from An Introduction to Statistical Learning with Applications in R. If you have not yet done this reading, please pause, go read that chapter, and come back. We will go over two primary topics in this lecture. First, we will go over permutation tests. Then we will go over the concept of bootstrapping. First, let's go over the concept of permutation tests. Permutation tests are a data-driven way of evaluating your null hypothesis. They are a new way of thinking about what your null hypothesis should look like and generating a distribution of your null using your data itself, as opposed to traditional parametric approaches that try to infer your null hypothesis based on a set of assumptions. So let's start by thinking about the null hypothesis itself. We'll do this by example. Let's say you are an electrophysiologist and you're recording from cells in the inferior temporal cortex. So you want to ask, do IT cells fire more to images of faces than objects? You do a series of recordings in cells in IT, and you look at the firing rates evoked when these cells look at pictures of faces versus objects. And you might get two distributions of firing rates, one for objects, shown here in orange, and another for faces, shown here in blue. Now, the way that you would evaluate this typically with more traditional statistics would be to calculate a t-statistic, to take the means, take the differences of the means, divide by the average standard deviation. And that would give you a statistic that you can evaluate against a hypothetical null distribution of these differences. So you'll see the t-statistic that you observe, which is t observed, based on the specific degrees of freedom that you have, which is determined by the number of observations you have in your sample, and see where that sits on a distribution of t-values that you would expect to see if the null hypothesis was true. And the null hypothesis in this case is that the difference in means is 0. So what you're evaluating is the probability that you would see this data, this set of differences, in your means if the real difference is 0. And you're working with an assumed distribution of differences, which follows a t-statistical distribution, so a t-probability distribution, which has heavier tails than a normal distribution. But otherwise, you can think of it as kind of a symmetrical normal-ish distribution. And so when you get a t-statistic and you do a lookup table where you calculate out what the p-value should be from that t-statistic, what you're really doing is taking a look at those calculated differences and comparing them against some untangible, untouchable null distribution of what you would expect to see if there was no real difference between the means. Now, this is the classic framing of what are known as null hypothesis test statistics. You do this with many different statistics: ANOVAs, correlation coefficients, t-statistics, chi-squares. They're all variants on the same idea. Take a framing of a problem, like a difference in means, and ask what's the likelihood that I would see these data if my null were true. And if the likelihood is very low, you reject the null hypothesis. This isn't the only way of evaluating a null here. An alternative way of doing that would be to ask this question using a regression model. And the same concept still applies. So we might fit a regression model like this, where I'm trying to fit the average firing rates per session, so YFR, as a model where I have my intercept term, beta hat 0, plus a regression term where I have beta hat 1 times a variable x faces, which is a dummy variable that codes 1 if the stimulus was a face image, 0 otherwise. And remember, since there's only two images, faces or objects here, that intercept term, beta hat naught, captures the mean effect of objects, and beta hat 1 captures the mean effects of face images. Now, our null hypothesis here really depends on the modulation of faces, so let's just evaluate that. So what you would do is you would calculate out a t statistic by taking the ratio of the regression coefficient with its standard error. That puts you back in this t distribution space. But here, you're still assuming that the effective faces, at least your null for faces, should be 0. But now the assumed distribution is that the value of beta hat 1 is 0. That's your null. And the goal for traditional null hypothesis test statistics is to infer whether or not the beta hat 1 that you observe is different than 0. But the assumption of how this distribution should look, the likelihood distribution of your data given that beta hat 1 equals 0, you still don't touch it. It's still some hypothetical distribution based on a set of assumptions. Now, an alternative way of asking about the null distribution is to simply generate one yourself. And this is how permutation tests work. Rather than assume the nature of your data and its links to some hypothetical null distribution, simply generate your null distribution using your data itself. Let's abstract our problem for a minute here. We'll just deal with x's and y's. In a standard regression model, your assumption is that variations in x does not associate with variations in y. As x changes, y doesn't change. That's your stripped down null hypothesis for a typical linear regression problem. How would you evaluate this in a data-driven way? Well, what you would do is you would first take the data that you have. So I have my sets of x variables, my y variable. I would calculate out regression coefficients. Let's just say this beta hat 1 observed here. That's the regression coefficient that you see in your data untouched. You set it off to the side here. So I have a range of potential beta hat values, which I'm calling beta hat star 1 here. And then I just hold off the actual observed value and put it on this line. And then what I say is, okay, if variation in x does not associate with variation in y, then the associations across observations is arbitrary. So why don't I just break that? So what I'll do is I'll do an iterative approach where I try many different variants of my experiment, but where I break the association between x and y. So I'll make a new data set on the first iteration. So we'll call this iteration 1. And what I'll systematically do is shift the rows of x. I'll just randomly permute different x observations, but I'll leave y alone. And what I'm doing is I'm breaking the linkage between observations in x and observations in y. And then I'll calculate out a new regression coefficient, and I'll keep doing this process over and over and over. So I'll run m many iterations where on each iteration I just randomly scramble the observations in x, leaving y constant. And then what I can do is I can generate out an actual distribution of data showing what the range of regression coefficients I would see if indeed the relationship between x and y were random. I now have a physical null distribution with which to evaluate my hypothesis. What this does is it maps across observations, or it breaks the mapping across observations between your predictor variable and your response variable, between your x and your y. And the null assumption is now that that mapping is just arbitrary. And so you build a data set, a distribution of effects, by making that true, by permuting across these observations. And you have m many now observations in this distribution of your null hypothesis. It's a discrete distribution, so you can calculate out your p-value directly. In this case, you would just count the number of times that you simulated in your random permutations a regression coefficient that was stronger than the one that you observed, and divide that by the number of iterations that you see, or that you ran. So in this case, your p-value can be discretely and directly computed, not estimated, but computed. Because you're just asking how many times in these random data sets did I see an effect that was stronger than the effect that I actually really observed in my unpermuted data. That's it. It's beautifully simple. Rather than infer anything about your null, make your null itself. So let's go through the algorithm for a permutation test. Remember, the goal is to directly calculate a null distribution from your data. So first, you calculate the observed effects in your data. We'll call this f hat observed, and set aside the relevant parameters for evaluating your hypothesis. In this case, if you're using a linear regression model, the terms in your linear regression model that are relevant for your hypothesis. Then you run m many iterations, where on each iteration you first create a new variable dataset, which we'll call x star, generated by randomly reassigning or permuting observations within variables relevant to your hypothesis. And I'll get to what I mean by within variables relevant to your hypothesis in a few slides. You calculate out a new model, which we'll call f hat star, that's calculated from x star. And then you store those relevant parameters of interest and put them off to the side. And you repeat this m many times, so you'll have m many observations of your parameters of interest. And then you directly compare the observed unpermuted parameters, that original, let's say, beta hat observed, against the distribution of parameters that were generated from the permuted set. That's it. It's a pretty simple algorithm, but it's incredibly powerful because now you have no assumptions about the nature of your data. You don't have to have normally distributed y. You don't have to have uncorrelated variables in X. There are no assumptions with permutation tests. The only thing that you have to pay attention to is the specific form of your null hypothesis. But in the implementation of your null, i.e. that the association between X and Y is arbitrary or random, that's it. That's the only assumption. So it's a very powerful way of determining the significance, the statistical significance of your effects. So for example, let's say you're doing a study. You want to know, does income level negatively associate with subjective stress levels after controlling for age? So the structure of your model would look like this. I have some outcome variable, which is a subjective stress variable, y stress. When a model is a function of the intercept term plus beta hat 1 times an income term. That's my target for my hypothesis, plus a nuisance variable, x age. Now in this model, my null hypothesis is only relevant to my target factor, income. Notice the framing of the question again. After controlling for age, does income level negatively associate with subjective stress level? So age is just a factor that we know impacts both stress and income. It's not relevant to our hypothesis, only that first term is. So what we'll do is we'll calculate out beta hat 1, which might get out to being, let's say, a value of negative 0.42, and we'll set it aside on this continuum of what beta hat 1 might be. Then what we'll do is we'll run a permutation test where we run m many permutations of my model, but in this case, what we'll do is we'll scramble the rows of the x income term, because that's the only term that's relevant for my null hypothesis. So the first one, we'll just permute the observations in x income, keep x age and y stress the same, get a regression coefficient, beta hat 1, set it aside, do it again, repeat that m many times, and then you take this vector of recorded regression coefficients for income and calculate out an empirical distribution. What you're seeing here is the directly estimated null distribution of your data if the relationship between income and subjective stress were truly random. This is no longer an intangible distribution. You physically have this set of m observations of your null distribution. And rather than infer a p-value, you can just calculate now your p-value. So let's say in this case, I had 164 observations where the regression coefficient was stronger, in this case more negative, than the regression coefficient I observed in my unpermuted model. I would divide that by the number of iterations that I have. In this case, I simulated 5,000 runs of the model. And so my direct p estimate is 0.0328. That's the probability of observing a more negative regression coefficient than the one that I actually observed in my unpermuted set if the relationship between income and stress was arbitrary. So there's this beauty to this. I don't have to assume this shape. I could have very wonky shapes in my null depending on the nature of my data. That's fine. All I'm asking is a count. How many times was it above or below this value? Now, the critical thing about permutation tests is that you have to think very carefully about what your null hypothesis is. You need to have this well-formed up front. Exploration with permutation tests is fairly limited. So you want to know which variables are relevant to your hypothesis and which are not. If we go back to the example in the previous slide, income was the relevant factor. Age was a control factor. So you only permuted income, not age. That means that the null model for my previous example was y equals an intercept term plus a regression coefficient for age, and that's it. The specifics of which variables you're controlling for and which variables you're targeting are going to determine what you permute. Permutation tests, as I pointed out before, have no assumptions on the shape of the null distribution. But scrambling assumes completely random links across observations, which may be inconsistent with some of your hypotheses or your data. So for example, permutation tests are very difficult to do in a time series context, where every observation of y in your system has some link to previous observations of y. And you might have some assumption that y covaries with some structure of x that itself also has this time series component. So you have to have some understanding of what it is about the relations across observations and whether or not a permutation test will be relevant for your question if you have some assumption in the nature of your data that requires some continuity across observations, even for addressing your null hypothesis. Also, permutation nulls may not necessarily have zero means. So you want to be aware of assuming that zero is the expected null effect. Especially when you're controlling for multiple factors that might be correlated with both y or your target variable, and depending on how you did your permutations, your null hypothesis distribution might actually have a non-zero mean. And that's actually a very valuable point of permutation tests, is that you don't even assume what the expected value of the null is. The randomization will tell you what your mean null will be. And if there are biases in your model because of the other factors you're controlling for or how you set up your model, the permutation test will reveal that and tell you what the true value of your null should be. But permutation tests require that you think very carefully about the structure of your model, the structure of your hypothesis, and the structure of your null hypothesis. Now, permutation tests are good for inference questions and asking what the probability of my data if some null hypothesis were true. There's another way to use these resampling techniques to determine the confidence of any parameter that you observe in your data. And that's the concept of bootstrapping. Bootstrapping primarily centers on confidence of your parameter estimates as opposed to structure of your null distribution. By confidence, what I mean is, what is the certainty of the value of a particular metric or measure? So I observe some value for a regression coefficient, a t-statistic. I want to know how confident am I in that particular value of that particular statistic. And we saw this in regression when we calculated out the model variance of your model and used it to calculate out a standard error for every individual regression coefficient. This standard error of your regression coefficient is an estimate in the confidence of the value that you fit for your regression model. If beta hat 1 is 0.5, is 0.5 most likely going to be the observed value plus or minus 0.2, 0.02, 3? So you want to acknowledge the fact that there's some degree of uncertainty in your parameter estimates and try to take that into account. Now in the regression context, this relies on some assumptions, right? We've gone over these before. Critically, in estimating the confidence of a regression coefficient in linear regression context, you're going to assume that y is normally distributed. In other words, the residual sums of squares are normally distributed. And that every observation of x, every variable in x is independent of every other variable in x. So for every xi, it's independent of every xj. With those assumptions met, you can use these equations to calculate out the confidence of your regression coefficient, assuming a normally distributed y and independent x. Now, this again is approximation. Just like the p-value from a t-statistic in the permutation discussion, this structure of your standard error relies on the assumptions of normality and independence. And if those are violated in some way or those don't work within your data set, then your confidence estimate of your regression coefficient is biased. It's not accurate. Now, in the same way that permutation tests were a data-driven way for determining your null hypothesis, bootstrapping is a data-driven way for determining your confidence in your parameter estimates. So let's stick with another hypothetical example just to see the logic of bootstrapping. Let's say, does hypothalamic stimulation increase cortisol levels? You have an electrode in the hypothalamus of an animal. You are recording circulating cortisol levels in the bloodstream, and you want to just see every time I stimulate, what's the evoked cortisol levels in the bloodstream. So you get a data table that looks like this. X is a binary variable for stim on that trial or not. Y is the cortisol levels after a certain period of time, after the stim or no stim, and you just fit a simple regression model that looks like this. Right? So your cortisol level is a function of some intercept term plus the regression coefficient against that stim term. Now, this gets me a regression coefficient beta hat 1. But if I want to estimate out what actual value, what potential ranges could beta hat 1 be, not if the null hypothesis is true, but just given this structure of variability in my data set, what you would want to do is you want to replicate your experiment. In an ideal world, if you wanted to understand the range of possible parameter effects, what you would do is you would replicate this experiment over and over and over and over again. You would create n many perfect replication experiments and then look at the distribution of those regression coefficients that way. But with bootstrapping, you can do that within your own data set. So what you do is you sample the rows of x and y together, one pole at a time with replacement. So I'll randomly select a row, and I'll take both the x and y values from that row, make a new variable over and over and over again. And by sampling with replacement, I might have some repeats of certain observations, and other observations might be missed. So in this first resampled data set, notice that 33.3 value observation paired with an x of 1, that gets pulled twice just by random. So I create a new data set that has the same number of observations as my original data set. But the key thing here is that the observations are consistent across y and x. So I don't break that association between x and y. So I calculate out my regression model for this new fake replicated experiment. I repeat that process m many times. So I'm going to have m many regression models. And then I store the relevant regression coefficients. So I'll have a vector of beta hat 0 and beta hat 1s from all poles of the bootstrap every time I run this bootstrap algorithm, which are kind of simulated reruns of my experiment. And I might get something that looks like this. Here we have empirical distributions and my regression coefficients for my model. So the intercept term, beta hat 0, is shown in that pinkish color distribution. The beta hat 1 is shown in that teal distribution. And from these distributions of regression coefficients, I can calculate out now my confidence intervals. So I can calculate out a 95% confidence interval for my beta hat 0 and one for my beta hat naught. And what this tells me is that, at least if I'm using 95% confidence intervals, that the effect that I observe has a 95% likelihood of falling in these ranges. So beta hat 1 could range between 5 and 16. This allows me to directly calculate out what my range of effects are by using this sampling with replacement to build new versions of my data set and retest my effect. You're essentially making a synthetic set of repeat experiments with this sampling with replacement model. So the algorithm itself is pretty simple. Remember, the goal is to simulate m many replications of your data set to estimate confidence of specific effects. So much in the same way as the permutation test, what you do is you run m many iterations, where on each iteration you create a new variable set y star and x star. So now you're creating new y's and x's, generated by randomly sampling observations, rows, from the original data set with replacement, keeping values across variables, columns, intact. You create a new model now, f hat star, that's calculated from these newly generated pulls of the bootstrap. All relevant parameters that you need, the regression coefficients, are stored. And now you calculate your confidence estimates. I use 95% confidence intervals. You could also calculate a standard error. You could do Bayesian confidence estimates, whatever you like. You just calculate it on the distribution of the target parameters of interest from those bootstrapped results. So this gives you an estimate of the confidence of the range of your effects. And you could ask inference questions. So if we look back at the confidence intervals for beta hat naught, beta hat 1 from my hypothetical experiment here, what you would do is, instead of calculating a p-value, you would ask if the confidence intervals in your bootstrap distribution include your null. And for simplicity's sake, we'll just assume that our null effect for our regression is 0. If it includes 0, or includes your null value, then you can't reject the null hypothesis for that effect, for that specific regression coefficient. It's a little bit different than calculating out a p-value, but it gets you the same place. You're basically saying, if I run this experiment 1,000 times, 95% of the time they're going to fall in this range. And that range doesn't include 0. So 0 is an unlikely value for this effect. It's data-driven. You're not making any assumptions about how that distribution could look. In fact, there are asymmetric confidence intervals, skewed confidence intervals, biased confidence intervals that you could get with bootstrapping. That there are many ways to handle it. But importantly, it's just a direct empirical calculation. You're just calculating number of times you see values that include 0 or not. Or you're calculating the actual width of your empirical range of your bootstrap distribution. There's nothing hypothetical about it. Now, there are just some things to consider when working with bootstraps, things to bear in mind. First, as both n, the number of observations, and m increase, where m is the number of bootstrap iterations, the bootstrap distribution approaches the real distribution. This is really just taking advantage of the fact that we work in a world where the law of large numbers exists. What that means is that there should be a value of m where the distribution that you get from your bootstrap is stable. So that every time you run a new iteration of the bootstrap, it doesn't really change the characteristics of the bootstrap distribution itself. This is a computationally expensive method. You're running many iterations of your analyses. So you want to think about choosing m such that you get a stable estimate of the bootstrap distribution, but you're not wasting cycles just adding to something that's already stable. You can also estimate bias in the bootstrap and in the model, actually, by comparing the mean of the bootstrap distribution to the original effect size itself. So if there's a big discrepancy between the mean, or the median of the bootstrap distribution, from the effect that you see in your original untouched data, that tells you something to kind of explore in a little bit more detail. Because you have control over the number of iterations of your bootstrap algorithm, there can be a huge problem using confidence estimates where they normalize by the number of observations. So for example, use of the standard error to estimate confidence on the bootstrap distribution. And remember, the standard error is your standard deviation divided by the square root of m, can lead to artificially high certainty with large M. You can run a billion bootstraps. What that'll do with the standard error is you're going to be dividing your standard deviation by the square root of a billion, which is a lot. And that denominator term starts to take over. And so you might have an artificially high degree of confidence, or you will have an artificially high degree of confidence in your parameter estimate that has nothing to do with the actual range that the value takes in the bootstrap. It's just because you're normalizing it by something that you have a lot of control over. So avoid where you can using things like standard error in the bootstraps and move towards standard deviations or things that don't fully rely on the number of iterations that you have. Another way to do this is just empirically calculate out where 95% of your observations that your bootstraps sit. Okay, we've gone over permutation tests and bootstrapping as two examples of resampling methods that offer a data-driven way of estimating confidence on observed effects and on inferences with regards to your hypotheses. These are very, very powerful tools that are commonplace in machine learning and data science and are gaining ground in psychology and neuroscience. They are non-parametric, so that you don't have any assumptions about the nature of your data in order to either evaluate your null hypothesis or estimate confidence. They can be done with almost any type of data. So they offer this computationally somewhat expensive ability to directly estimate things that traditionally we have to approximate or estimate hypothetically. So I highly encourage using bootstrapping and permutation tests as the default methods for assessing confidence and your null hypothesis in your data sets, in your empirical data sets.